everyone, welcome back to our YouTube channel Becoming a Rose Developer. I'm Desire and today we've got Lathika who has just completed the course Python Basics for Robotics and she'll be giving us a presentation on that. So without any further ado, I'm going to hand over the platform to her so that she can begin her presentation. Alright, whenever you're ready,
Uh,
Lathika.
Yeah, so I'll just get started with the real robot.
Alright.
Um,
Alright, can you explain to us what you're doing?
so first I'll just get the simulation started, like along with the real world demo over here. So yeah, let me. So first I'll be demonstrating the um, no class Python program.
Mm-hmm.
This version does not include the uh, object oriented programming approach
Mm-hmm.
for the um, navigation functions. So, this is the entire code. It has all the navigation functions, which includes the robot movement functions, the laser scanner functions, and the odometry functions.
Mm-hmm.
So I'll just demonstrate it real quick. Uh, okay. This version, let me just. So this shows all the movement um, navigation first. So like forward, backward, and then it's supposed to turn right and then turn to the left and then go forward and backward, like timed as well, like timed
Mm-hmm.
rotation.
Mm-hmm. I haven't
Yeah.
seen it do that. What's going on there?
Uh, yeah. Mm. Uh, Let me just run it again once.
Okay, alright. Okay, it
Um,
doesn't seem to do as expected.
mm,
All right, let's do this. Try your
yeah.
other script, the class division. I believe that one is more advanced than this one. Let's see if that works on that one.
Okay. So I just launched this simulation thing again. Mm,
So this one is the one that is supposed to have an obstacle avoidance implementation, right? Okay. All right. This seems to work well. Okay, that's good. Let's try the other one more time.
okay. Um,
Are you sure it's not too close to that? Okay. All right. No worries. It cleared it.
hmm. Um,
All right. Clearly, there's something going on with this one because it's not executing the
yeah,
10 rotations.
yeah.
Right. Okay. So this script needs review, although the obstacle avoidance one works well. Anyways,
Okay.
you can stop execution for this one. I have a few questions that I want to ask you before we get into the presentation, right?
Okay.
So there is this window that you keep launching, right? The one that's on the left, and you keep calling it the simulation. Do you fully understand what is the purpose of that window?
So the purpose of that window, I think that it gives a simulation, like the simulation of the real bot on the like online.
Okay, so the
So
okay, let's correct something
I
here. When you are connected
mhm,
to the robot, right, you do not have anything to do with simulation, right? The reason you use a simulation is as a substitute for the real robot, right?
yeah.
Now, we specify in that notebook the actual reason why you need to launch that script, right? It's not a simulation that you're launching, it's you're launching an
Mm,
RFIS window, right?
mm.
Right. Do you understand what RFIS is? What does it do in relation to your project?
Like as far as I've like learned, like
Mm-hmm.
doing all of this,
Mm-hmm.
when I used it for the like Turtlebot simulation,
Mm-hmm.
that's where I could see. Okay, no, that's actually a different window. I don't think it's a simulation window. So yeah, I'm actually pretty. I'm not sure about what it actually is.
Okay, you must look it up. In the notebook, it's there, right? So I can give you an idea, but you have
Mhm.
to find it for yourself. Why do you need to have that window there? You can run your program without having it there, right? Do you understand that?
Mhm. Yeah.
Yes. So it's serving a completely different purpose, but you have to find out why it's doing that. Anyways, I'm going to allow you right now to switch to your slides, and then you can give your presentation. Then we'll ask a couple of questions towards the end, okay?
Okay.
All right, let's go for it.
Okay. So uh, Good afternoon, everyone. I am Lathika, and today I will be presenting my Python for Robotics project. So, the objective of this project was to develop and test robot control software using both procedural and object oriented programming approaches, and then implementing them in both the simulation and on a real robot platform. So this project was tested using the Turtlebot 3 simulation and the FastBot real robot.
Mm-hmm.
So in addition to implementing the control functions, I developed like three autonomous algorithms, which was obstacle prediction, direction tracking, and naive obstacle avoider.
Mm-hmm.
So I'll get into the project overview first. So it's mainly divided into like three parts. The non-object oriented programming version or approach, the object oriented programming approach, and the robot algorithms. So for the first one, we have 30 robot control functions. So these include 14 movement functions, 13 laser scanner functions, and three odometry functions. The second one is the object oriented programming version. It includes the same functionality, but all of the functions reside inside a robot control class, which makes the code like cleaner and reusable, and it's much more modular.
Mm-hmm.
And thirdly, we have the algorithms. So the three algorithms which I implemented are the obstacle prediction, direction tracking, and the naive obstacle avoider. So all these algorithms were tested on the fastbot robot. So next, I'll move to the difference between the non-OOP and the OOP versions. So in the non-object oriented programming version, the functions are written independently and they rely on a global robot interface. This means that the interface must be passed or accessed repeatedly like throughout the program. So we have to keep calling the robot interface every time we need it to do the call the function basically. So in the object oriented programming version, all the functions are encapsulated inside a robot control class. So this robot interface is stored once during initialization using the self.ri, which is basically an object. We keep calling the object instead of the entire function again and again. So
Okay.
it is accessible throughout the class. So this object-oriented programming version improves modularity, maintainability, and scalability, and it is much preferred over the non-object-oriented version. So next we move on to the algorithms. So the first algorithm is the obstacle prediction algorithm. The algorithm begins by collecting all laser scan readings from the LiDAR sensor present on the fastbot robot. Instead of processing the entire 360-degree scan, it focuses only on the frontal 90 degrees because the obstacles in front of the robot are more relevant for immediate navigation. So firstly, all the infinite values are removed because they indicate no detected object within the sensor's range. And then the minimum distance is calculated. If the minimum distance is greater than zero point 0.5 meters, the robot predicts that there is no nearby obstacle. If the distance is less than zero point 0.3 meters, I used Python's multi-mode function from the statistics library. Multiple modes generally indicate a discrete object, while a single mode um, indicates like a flat surface like a wall. So multiple mode allows us to like differentiate between uh, the obstacle being either like a object or like the
Mm-hmm.
wall.
Mm-hmm.
So
Mm-hmm.
that's for the obstacle prediction algorithm. Secondly, we have the direction tracking algorithm. Yeah. So here the robot obtains its orientation from the odometry data in the form of yaw. The yaw values range from negative pi to positive pi radians. So to provide a representation of the orientation, the entire 360 degrees range has been divided into 16 equal segments
Mm-hmm.
of 22.5 degrees each. So each segment corresponds to a compass direction like north, northeast, southwest, and so on. So whenever the robot changes its orientation, the algorithm maps its current yaw value to one of the 16 directions.
Mm-hmm.
Uh, uh, and next we have the obstacle avoider algorithm. So this basically uses the LiDAR scan values. The LiDAR scan is divided into 8 sections of 45 degrees each. However, only the front 5 regions are used because they directly influence the movement decisions. So it is a really simple rule-based approach. If all the front sectors are clear, the robot moves forward. If the frontal left region is blocked, the robot moves turns right, and if the frontal right region is blocked, the robot turns left. And if the entirety of the front region is like blocked, the robot compares available space based on the yaw values and turns towards the more open direction. So during the execution, the algorithm also continuously tracks the robot's total distance using the Euclidean distance calculation along with its current distances and the obstacle prediction.
Mm-hmm.
So there were three challenges that I faced during development of this project.
Mm-hmm.
So, firstly, the scan index differences. So, the scan indices differed between the simulation and the real fast board robot. So in the simulation, the front direction corresponded to the middle of the scan array, whereas on the fast board, it was located at index 0. So I had to implement an angle to index function that uses actual scan angles instead of hard-coded indices. So to convert the angle to the correct index. Secondly, the robot not turning on the real robot. So the angular velocity used in the simulation was way too low for the physical robot. So I had to test it quite a bit, and I determined that 1 radian per second was the minimum reliable turning speed. And
Mm-hmm. Okay.
thirdly, like um, empty data like during startup was when sensor data was not immediately available, it would not run properly. So had to implement a wait for sensor data function so that it ensures valid scan information is received before the robot begins its operation.
Mm-hmm. Okay. Okay.
And so to conclude this project successfully, I wouldn't say successfully because the no class version didn't like run as expected, but like for the class version, I implemented the robot control software using both the using the object-oriented programming approach.
Mm-hmm.
So three autonomous navigation algorithms were developed and tested both on simulation and on the real passport robot. I learned quite a lot, I'd say, about ROS to LiDAR processing, object oriented design, and odometry functions. So, yeah, that's all I have to say.
Mm-hmm.
I'd like to answer any questions you might have. So, thank you.
All right. Thank you very much, Lathika. So, very nice presentation, by the way. So, let's let's get into the questions, right? So can you switch to your screen that has got your object, right? So I want us to have a look at your obstacle avoidance script, right? Specifically, I want us to look at the processing of ranges data, right? So you spoke about having to make angle, having to convert like indexes to angles, right? Um,
Yeah.
that's a very important thing to do, by the way. So can you explain us in more detail, like break down the function and how you did that, so that we get a clear picture of what you did exactly?
Mm, mm,
Do you know the name
mm,
of your function that does that?
yeah. Let me just look it up really quick.
You,
Um,
if you know the name, you can do Control F and then you type in the name, then it will take you exactly to where that function is.
yeah, it was angle to index.
Okay. So keep typing and okay, there we go. Yeah.
Okay, so I did use AI to help me understand the ROS2 concepts,
Mm.
LiDAR processing, and object-oriented design patterns.
Mm-hmm.
So I like to adapt the code uh, to fit the fastbot platform, debug all the sensor issues, and fine tune the speed and stuff so that it would work.
Mm-hmm.
So, but I did learn quite a lot from it. So I'll try to explain how much I can. So
Yeah, let's go for it.
yeah,
That's the important part, right? That's what we want to get. We want to make sure you understood that the tool is there, but show us that you understood what it did.
okay. So the angle to index, it takes in two inputs, self and angle, and the two parameters. Self is the object that we are calling like for the robot. So an angle is the angle that it receives to turn it into the index that we want. So we have an increment, minimum angle, max angle, and the range,
Mm-hmm.
which we get in the robot control library. Like we import it at the top, and then we use those inbuilt functions to get all these values.
Mm-hmm. Mm-hmm.
Um, and then I had to add this safeguard feature so that it wouldn't give an invalid answer, like so that there would be no errors. And so the angle would be wrapped between the minimum angle and the maximum angle window.
Mm-hmm.
So if it isn't, if it is not within the range, it would be considered invalid, and we
Mm-hmm.
wouldn't get like the appropriate index for it.
Mm-hmm.
So that is what this code is. And then we just use the math functions from Python library to round off and get an integer value for the index
Mm-hmm.
using this wrapped value. And then we just get it from the range of the
Mm-hmm.
indices that we have.
Okay. Okay. All right. So, can you? Hmm. I wonder if you can explain. Now that we're talking about this, can you explain what might have been happening with the robot in the non-class version, right? Obviously, there's no processing of LiDAR scan there, but
Mm.
I'm keen to know, did it work for you when you were testing it? Did it manage to
It
go forward and
did.
backwards and rotate?
Yeah, it did work, but I am not sure what exactly happened in the non-class Python
Okay, so
because it has all the moments like laid out. So I am not exactly sure why it didn't run.
and
Uh,
okay, so you have got your functions that you're calling, and I'm assuming you're setting angular velocities there. Okay.
yeah, linear and angular velocities.
Yeah, yeah. All right. All right. All right. You have got some work to do there. Anyways, there's one thing that I wanted to ask you, which was in
Yeah.
relation to interfaces, right? So when you're describing an object, right? You mentioned something about the interface being already there, right? So I think there's something a bit off there. What do you understand by the term object? Like
So
in the terms of the language, yes.
so object is how do I compare it? Okay, so basically we have like a function, like a class.
Mm-hmm.
So an object would be like a part of the class, basically. Like instead of calling the, we have like certain functions within the class,
Mm-hmm.
and if we wanna run the function, the set of functions,
Mm-hmm.
instead of calling them individually, like one by one, we can just call the object once, and that would like run all the functions within the class,
Right.
kind of.
Okay. Okay. So what does the object contain, right? I think if you can define what is an object in terms of the things that it has got within itself, things will be a lot easier. So if I ask you one more
Um,
time, what is within an object, right? So when you say I have an object in memory, um, there are two things that you expect your object to have, right? To be a, if maybe even one, but what what are
mm,
those things?
uh, so like an object would basically be, we can like assume it to be like a child and a parent kind of situation, like where the entire class would be the parent and the object would be the child, so that you can like
Okay.
um
Okay, let me stop you there. I think you are on the right path, but you're pulling things apart with which are supposed to be together, right? When you create a class, right, you define methods and you define the data, is in member variables or whatever data your class is going to hold, right? So you've got methods and data, right? And those things make up they compromise, they make what is called a class, right?
yeah,
And then when you instantiate that class, so do you understand what instantiation is?
initialize.
Right, something like that, right? So when you do that, what
Yeah.
happens, right?
um,
When you
so
initialize your
it
class,
basically
what happens?
it calls the like constructor. If you have a constructor, it calls all the like methods in the constructor. Yeah.
Mm, yeah, well, close, yes. And then what is the thing that you end up with after calling the constructor?
uh, it just performs all the functions present in the constructor when you
All right,
call an object.
all right. So let's sum it up, right? Um,
Okay.
is you do understand the code that you've used. I think I can see that there are some things that are a bit missing, right?
Mm,
And this the understanding of what happens when your class is instantiated, right? That is the creation of the object itself, right? So your object is
yes.
created with all its member variables. Maybe they are initialized or they are initialized to variables that are default to given values that are default, right? But the
Yeah.
thing that comes after that initialization is what you call an object. So a it is exactly what is defined by your class, right? But it's an instance of that class, right? So a class is a template of creating objects, okay? So
Yes. Yeah.
very important things to understand. And we look for these things when you come for evaluation, right? You must be able to fully differentiate
Yeah.
and understand them, right? So I would say you got your code to work, and that makes for a well-running project, right? However, these fundamentals need to be polished for you to keep progressing on
Okay.
your Python Python journey. All right. So what I'm gonna do here is I'm gonna wrap up our conversation here, and then we can finish our conversation on Zoom. All right. All right, everyone. This was Lathika's presentation, and would like to encourage all those of you who want to try this project to also do the same, and you can come and showcase your work here.